Alright, so we'll begin Chapter 6 here with 6.1, and hopefully a lot of this is review. We do see a few maybe more complex problems in here though. So probably a few that you need to pay attention to, but like I said, hopefully most of this section here is review for you guys. But anyway, let's get to it. So what does it mean to be uniform circular motion? This is definitely, hopefully, a review. Uniform circular motion, right? The key there is uniform. Uniform tells us that it's moving with a constant speed. And so there's no tangential acceleration. We'll look at that a little bit more in this section. And then it also tells us that we always have to have a centripetal acceleration, right? So the key here is we're moving at a constant speed but not a constant velocity, because we know that at any instant in time the velocity is actually changing, right, as we move our way around the circle. So the velocity is constantly changing, and because the velocity is changing, I have to have an acceleration. And so even if it's uniform circular motion, I always have to have centripetal acceleration. So make sure we don't forget about that part of it. But anyway, we'll see those kind of crop up in some examples, and I think you guys will agree there's nothing too tricky there to do. But anyway, let's look then down here at this part. So if the period of the uniform circular motion is t, and keep in mind the period is how long it takes to complete one cycle, how can we find the speed of an object in uniform circular motion? So if you guys remember back to last year, we had some orbital velocity equations for the velocity of an object in orbit, and we'll get back to that later. But if ever in doubt, keep it simple, right? If I know the period is t and I'm talking about uniform circular motion, well, how far does it go in a single period? Well, it goes one lap around the circle, right? So if I'm looking for my speed, if I'm looking to find my speed for uniform circular motion, the easiest way to do it is just take 2 pi r, the distance that we go as we travel around the circle, and then divided by that period. So a lot of times if the questions, maybe if you can simplify them down to this, makes it a little bit more manageable than jumping in with some of our orbital motion and so. Anyway, so let's start off then with example 1 here, a pretty good review example. So a 4 centimeter diameter, so that tells me the radius is then 0.02 meters, right? Turns at 2400 RPM, and the biggest thing that you have to watch out for here are the units, right? RPM stands for revolutions per minute, right? So revolutions per minute. When we deal with this, a lot of times we need our measurements to be in terms of radians per second. So we'll see that as we move through this one. What is the linear speed of a point on the surface of the crankshaft? So again, we've actually seen this if we go back even earlier this year. We talked a little bit about our uniform circular motion in chapter 4, I believe it was. But anyway, let's go back and review this. So again, the first thing I want to do is go ahead and convert the 2400 RPM. So I'm going to convert that then to radians per second. So again, 2400 revolutions per minute. Hopefully you guys are all pretty good with your conversions, but if you need to see this once or twice, I will work it out here for you a few times. So 1 revolution is 2 pi radians, right? We know there's 2 pi radians per trip around the circle, and then obviously 1 minute is 60 seconds. So setting it up this way, right, dividing 2400 by 60 would give me 40, and then 40 times 2 pi would be 80 pi. So I'm going to go ahead and leave it in terms of pi, but it's 80 pi radians per second. So that's my conversion. So then we just have to find out what is the linear speed of a point on the surface of that crankshaft. So again, this kind of ties in with the main theme of this first section, and that's tying some of our angular measurements, right? I've got my angular velocity here. How do I relate that then to my linear velocity? Well, again, this is something we're going to review a little bit more, but hopefully some of us remember that the linear velocity is just equal to the radius times the angular velocity. So my linear velocity, again, is the radius times the angular velocity. So since I know the radius of the crankshaft and I know the angular velocity, I just have to take 0.02 times the angular velocity of 80 pi. Right, so I just have to calculate that, and that will give me my linear velocity. So then if I leave this in terms of pi, it ends up being about 1.6 pi meters per second. Obviously, you could go ahead and calculate that as well. I will leave that to you guys to do that, but 1.6 times pi, you could approximate that to be about 5 or whatever it ends up being. But make sure you're pretty comfortable, again, converting linear speed from our angular motion here. And we'll see a lot more of this as we move through the section. Okay, so I already alluded to this obviously on the first slide, but why is there an acceleration if the speed is constant in uniform circular motion? And again, the key here is the fact that the speed is constant, right? If the speed is constant, it doesn't necessarily tell me that the velocity is constant. And in fact, we know as we go around in a circle, the velocity is constantly changing direction. Right at the top, the velocity would be going this way, point over here, the velocity would be going that way, and so on and so forth. So the only thing we know for sure is the velocity is constantly changing direction, but it's not changing magnitude because the speed is constant. So the reason there has to be an acceleration, though, is I still have a change in velocity. Because I have a change in direction, I have a change in velocity. And we know if we have a change in velocity over time, we have an acceleration. So again, we have to have an acceleration, and we know that that acceleration in this case for uniform circular motion is centripetal acceleration. The reason I'm stressing this so much, I hope and know that you guys are already pretty comfortable with this. But we'll see some of those questions where they ask us to find the acceleration of an object as it goes around in a circle. And one of the biggest themes to watch out for is don't forget that it always has a centripetal acceleration. It might also be accelerating as it goes around the circle, but it always has to have a centripetal acceleration. So I know one of the biggest mistakes that students in the past have made is they get so caught up by finding that tangential acceleration, which we'll look at moving forward here, but they get so caught up finding that tangential acceleration that they completely forget about the centripetal acceleration, but we know it has to have that. So anyway, that's enough of a side note on that, but again, a very, very key concept for us. Anytime we're moving in a circle, it has to have that centripetal acceleration as well. So on these next couple slides, I'm going to redefine hopefully something we're already comfortable with here, but again, it's a relationship between linear and angular measurements. So we use theta to represent the angular position. How did we first define theta, though? How did we first define radians? And actually that goes back to pre-calculus. Hopefully you saw this and remember this, but when we first define radians in pre-calculus, you define it as the arc length, which oftentimes they'll use an S, over the radius. So 1 radian, 1 theta, is when the arc length and the radius are the same length, right? That's when we get a proportion of 1 over here. So anyway, this is the definition of a radian. A radian is the proportion, the ratio between the arc length and the radius. That also makes it really clear to see why radians are a unitless measure. Right? If I think about the arc length and the radius, both of those would be in the same unit, whether they're centimeters or meters or whatever. They'd be in the same unit, which would then ultimately cancel out as I find this ratio. So sometimes that helps to define why theta is in terms of radians, which is that unitless measure. But anyway, what this allows us to do then is more generically define the arc length S in terms of theta. So obviously if I just solve that equation up there, I get S equals R theta. Now again, for the most part in this course we'll use, instead of the arc length, we'll use X as our position, right, and then R theta as our radius and our angular displacement. So anyway, the first of our 3 really relationships between linear and angular measurements. Our linear displacement is equal to the radius times our angular displacement. So we'll see the other 2 here in just a second. So we've seen angular displacement. Let's talk now about angular velocity, right? So how did we first define angular velocity? Well, we first defined it the exact same way we defined linear velocity. We know linear velocity is just the change in displacement over the change in time. The angular velocity is the exact same derivation here. The angular velocity is just equal to the change in angular displacement over the change in time, right? Or more formally, just change in displacement over time. So that's how we first define then the average angular velocity. We'll see a few other relationships for this, but sometimes keeping it simple is the route to go. So how do we define then the instantaneous angular velocity? So again, this goes back to kind of some of the calculus involved, but if I'm looking for the instantaneous angular velocity, what I'm really looking for is the angular velocity, right, as the time approaches 0. So the limit as the change in time approaches 0. And there's 2 ways that we work with this using calculus. One way is going back to graphs. If I give you some function that represents the position, so if I give you t squared minus 3t plus 4, whatever it may be, right? So if I give you some function that represents the position, then the instantaneous velocity would just be the slope at any instant in time, right? So it would be the slope at any particular point on that graph. So keep in mind how we can do it graphically. Also, if I gave you the function, how could we find the instantaneous angular velocity? Well, again, if I gave you the function in terms of time, then the instantaneous velocity function would be the derivative of that function, right? So because we're finding the slope, it'd be the derivative of that function. So really nothing hopefully too new here. This is all a review of the same relationships we already know. But if and when you see those questions in the homework and the example page here that give us a function for t, if they ask us to find the angular velocity or the angular acceleration, the big thing you have to be comfortable with is the same relationships that you guys already know are still true for our angular displacement, velocity, and acceleration as well. And finally, with the angular velocity, before getting into maybe more complex situations, how does the angular velocity relate to the period? And again, I throw this in because I think sometimes we tend to overcomplicate this. Right? Angular velocity is in its simplest form change in displacement over change in time. So if I know the period is the capital T, right, I know that's the period for an object, what is the angular displacement for one period? Well, the angular velocity then would be the angular displacement of 2 pi, right? That's how many radians it goes in one period. So again, sometimes keeping it simple can be the key to these problems. And in this case, the angular velocity again equals 2 pi over t over the period of the motion. So that's something helpful, again, keeping problems simple. But anyway, the other note that I threw in down there, probably good to kind of read through that. A particle moves with uniform circular motion if and only if its angular velocity is constant and unchanging, right? So it's only uniform circular motion if its angular velocity is constant and unchanging. So notice with the angular motion we can use velocity, whereas with linear motion we have to use just speed, right? Because the angular velocity is constantly rotating the same direction at the same rate in uniform circular motion. Okay, so probably the last thing we'll see then in the first part of the notes here, and this is definitely one of the new parts, so I pay attention. Don't freak out too much as you go through this. If it's a little bit confusing, you're welcome to come in and get some help from me if you need it. This is not necessarily something you would have to reproduce on your own, but I do think it's helpful to see, and it's something that we didn't really see last year. So how are we going to derive the centripetal acceleration by using some calculus? Well, we know what the equation for centripetal acceleration is, right? The equation is v squared over r. We've known that since last year. We've seen it. We've worked with it. Not too bad. But again, the question is, where does this equation actually come from, right? How come it's v squared? How come we're dividing by the radius, right? Where is that actually coming into play? So we're going to use some calculus to see where this is coming from. So anyway, as always, when we start with a lot of these definitions, we know that the acceleration is the change in velocity over the change in time, right? So the acceleration is dv over dt. Well, if I break this up, what does dv really mean? Well, dv again is the change in velocity, right? So if I kind of blow up looking at this picture here, the change in velocity, right? My change in velocity would be the difference between that initial velocity vector and that final velocity vector after a certain period of time. So that change in velocity would be kind of this measurement up here. Well, to define that change in velocity would just be whatever the velocity, whatever that radius of the velocity is, whatever the magnitude of that velocity is, right? So it'd be the length of those two vectors, which I'll just call v, and then it'd be times the change in theta, right? If I had those numbers, I could find this change in velocity right here. So dv is just my, again, velocity d theta. So it's now in terms of d theta. So I'm going to do the same thing as I look at dx, because I know that velocity, so v, is dx over dt. But again, if I'm thinking in terms of this measurement down here where dx is representing the arc length, we use the same type of rationale. We know the arc length, the change in arc length, would be the radius times d theta, times my change in the angle. That's actually the relationship we know for our linear measurements. So then my velocity ends up being r d theta over dt. So this is what I'm ending up with for my velocity. So then, since I have dv solved for v d theta, I'm going to go ahead and solve this equation. So v equals this, right? V equals r d theta over t. I'm going to go ahead and solve that for dt. So if I do, I end up with dt equals r d theta over the velocity. The reason I did that is now I can take both of these measurements and substitute them into my acceleration function, right? So my acceleration equals v d theta over r d theta over the velocity. And what I end up with here, if I flip multiply the bottom, is I get v d theta times, again, the reciprocal of the bottom, so v over r d theta. And obviously from this point we can see the d thetas cancel out, so I have v times v, or v squared, over r. So from this I get the centripetal acceleration v squared over r.